This experiment is measuring atomic spectra. Basically, as you know, different elements, mercury, helium, lithium, and here hydrogen, they produce different spectral lines when atoms are excited by electric fields. And exact same lines are actually absorbed if you shine a continuous spectrum of light at those atoms. So those are special energy values for which electrons are either emitting or absorbing energy in these atoms. So in this experiment, what you do is you put a spectral tube in between two contacts. There's a lot of voltage there. Flip the switch, and this happens to be helium, starts shining an electric field with all those lines mushed together and coming at us in our eyes. This a little spectrometer can split those lines into different angles, and we can observe them as different separated lines of different colors. So what this is basically you're looking with this simple microscope at the light that helium emits. It passes through a diffraction grating, which is basically a glass with a whole bunch of scratches put on it, very, very fine scratches, micrometer sized, and it acts as a basically an interference device with many slits, which amplifies interference effect. And all of these different, although it's called diffraction grating, I mean, you might wonder why diffraction and interference, two different words for similar effects, but because basically it's diffraction and interference are the same thing, just two different manifestations of the same effect. The point is, this produces diffraction fringes or interference fringes on each side of this central line. So if I'm looking at this thing, right here would be central line, and from this diffraction grating I would have spectra split into different angles going outward, sideways, like this, which can be measured by this second piece of this microscope. So you can move it for different angles and start seeing lines emitted by helium as a function of an angle, which you can measure right here with the use of this little device. You would have basically several spectrum on this side for diffraction m equals 1, another spectrum m equals 2, and they keep going because for different angles you have more and more diffraction maxima. And the same thing on the other side. M equals 1, you put it farther, m equals 2, and so forth. So you would measure all the spectral lines coming from helium several times and measure what angles they are at, depending on what you see in this eyepiece right here, and what their angles are with respect to the sort of central axis of this apparatus. You should be able to see basically all spectral lines from different gases that you would measure. You would measure hydrogen, helium, and mercury. So for example, for hydrogen, we should be able to see, I don't know if you can see in this video, we should see a red line, we should see a blue line, and two purple lines. You would measure those, and you would try to fit those measurements into a formula derived by Niels Bohr for a hydrogen atom, for energy levels in a hydrogen atom. And what you would be able to see is that these measurements for hydrogen work remarkably well. But you add one more electron to an atom, helium, like this thing, and immediately Bohr's model breaks down, and the spectrum of helium looks nothing like spectrum of hydrogen. Bohr's model does not describe it at all. And if you go to mercury, it's even more complicated. Mercury has 80 electrons, I believe, so it's even farther away from hydrogen. So the point of this experiment for you is then to look at how Bohr's model describes hydrogen atom really well, and you can see the spectrum and describe the spectral lines very well, but at the same time fail for the second atom on the periodic table, which is helium, and basically everything else. You need something far more sophisticated than Bohr's model to understand how those atoms emit light. But this is sort of a first step in spectrometry. That's it. The data will be given to you.